So I have my net total rate of heat transfer minus my net total rate of work being done by external things like shaft work or electrical work. And now I know that I also have flow work being done by the fluid as it pushes its way out into the control volume. I also have flow work being done by the fluid as it pushes its way out of the control volume. I have the time rate of change at which energy is being stored in my control volume, and it could be stored in forms of internal energy, kinetic energy, and potential energy. I also have the rate at which energy is being carried in and out of the control volume by the mass flow, and I'm writing this on the right-hand side, so I have positive what's leaving. I subtract the integral of what's coming in. Okay, let's continue to group like terms. I see on the left-hand side in my flow work, I have an integral with respect to mass flow rate across my boundaries. On the right-hand side, I also have integrals with respect to mass flow rate of energy being carried across my boundaries. Let's group those together and see if anything interesting happens. Okay, I'll have my first grouping here. The integral of all mass flow leaving, and I'll write it this way. Internal energy, here's my flow work, pressure times specific volume. Here's my kinetic energy. Here's my potential energy. Here's the integral of everything coming in across my boundaries. Internal energy, here's the flow work term, pressure times specific volume. Here's kinetic energy. Here's potential energy. Maybe now you're seeing, wait a minute, I've got internal energy plus pressure times specific volume. This is the thermodynamic definition of enthalpy. So for a control volume, enthalpy is the combination of internal energy and the flow work. So the energy carried by the fluid in terms of its internal energy and the work being done by the fluid as it enters and leaves the control volume. The sum effect of those two components is enthalpy for an open system. Okay, and note, this is still internal energy. So note there is no PV term since this is energy storage. Okay. So looking at these terms, going from left to right, again I have the energy transfer, the net energy transfer via heat. The next term is the net energy transfer due to work between the system and the surroundings in its various forms. Could be shaft work, could be electrical work, are the two usual things. The next term is the time rate of change of energy storage inside my control volume. And then the last two terms look like the sum effect of energy being carried by my fluid as it's crossing the flow boundaries. And that can be internal energy, energy stored, kinetic energy, potential energy, flow work. All of those things together. Now this is a pretty complicated expression, and we're probably going to want to use some simplifications to enable easier analyses. So let's try to look at some assumptions we can make. Oops. Simplifications. Okay. One of the most common is assuming we have a uniform state. By uniform state, I'm saying the energy storage term is an integral over the mass of the control volume. And when I say uniform state, what I'm saying is that inside this control volume, the internal energy is the same thing here as it would be here, as it would be here, as it would be here. I'm treating my control volume as this black box. You could think of it as almost averaging everything out inside my control volume. My state is uniform inside the control volume at any instant in time. So this simplification then just looks like the mass of the control volume times the average energy level of the control volume. That's uniform state. Another assumption I can usually get away with making is locally uniform one-dimensional flow across my boundaries. In that case, I'm saying my integral over an inlet or outlet. I'll write it now in terms of the enthalpy. Remember, my mass flow rate looks like the density of the fluid, the speed of the fluid, the area over which the fluid is crossing the boundary. If I'm assuming it's locally uniform, then I'm assuming the properties are constant over that inlet or outlet. And if it's 1D flow, I'm assuming the speed is uniform over that inlet or outlet. So going back to my description here, if this were looking like a pipe of some sort, I would be saying across that boundary, my speed is the same, my density is the same. I might have different speeds and different properties at different inlets and outlets. That can still occur, but I'm saying at that specific portion of the boundary, I have uniform properties and I have uniform velocity. If that's the case, then this integral just simplifies to the whatever the sum is over all of the inlets or outlets of the mass flow rate times the total energy of the fluid. And again, that enthalpy accounts for energy storage through internal energy and the flow work that's occurring as the fluid's entering and leaving my control volume. Okay, so incorporating those, I would have uniform state, uniform flow. This makes my first law look like heat transfer work on the left-hand side, on the right-hand side, time rate of change of energy being stored in my control volume mass. How is it stored? Internal energy, kinetic energy, potential energy. The sum of all energy leaving my control volume, the sum of all mass flows and energy level of those flows minus the sum of all mass flows in, their energy levels. Okay, this hopefully looks a little bit simpler to use. Other common assumptions I can make would be steady state. If I'm at steady state, then all the energy, the rate of energy that's entering my control volume perfectly balances with the rate of energy leaving my control volume, and therefore there's no change in energy inside my control volume with time. So the time derivative term goes to 0. That would make this entire term go to 0, for instance. Let's see if there's any other things I can usually assume. We'll see a lot of control volumes, not all of them, but in many cases we have negligible changes in kinetic energy and potential energy. In that case, we would have, let's see, I'll write it this way. Negligible changes in kinetic energy, those terms would, negligible, they're smaller than the other terms, and they're small enough that we can neglect them, not consider them in the analysis, because they're not changing as much as other things. And again, that would depend upon the nature of the thermodynamic device you're looking at. And that's what we'll be doing in the next several classes. Okay. This is our usual workhorse, the place that we start for uniform state, uniform flow. We can usually make those assumptions in this thermodynamics class, and then we can further apply other assumptions as they apply to the problem, sometimes steady state, sometimes negligible changes in kinetic energy and potential energy. But there you have it, in all of its gory, wondrous detail, the first law of thermodynamics as it appears for a control volume. And the last thing I'll say is you might think of this, how it compares to the first law of thermodynamics for a closed system. What we have differently is really these last two terms on the right. The accounting for the energy of the fluid as it's entering and leaving the control volume, and that includes fluid work terms hidden there in the enthalpy, and other energy storage terms such as internal energy, kinetic energy, and potential energy. Thanks so much.